Hello everyone, today we're gonna continue our tree data structure series, part 2 out of 5. In this tutorial, we're gonna talk about binary search tree, the balanced binary search tree, and the unbalanced binary search tree, and the value of these property bring. We're gonna need some context about tree and binary tree, so make sure you check out part 1 if you haven't done so. This tutorial is a part of the data structures and algorithms class. First, we're going to talk about some properties of binary search tree. Binary search tree is a fairly simple data structure. There are only two constraints that we need to remember. First, a node can only have maximum 2 child nodes, left child and right child. And the second constraint is the left child has to be smaller than the parent node and the right child has to be bigger than the parent node. These two constraints are enough to set up the automatic insertion and deletion for a binary search tree. Whenever we want to insert or delete a node, we can just call these two methods, as opposed to tree and binary tree that you have to do it manually. For insert, if the node that we're inserting is smaller, we're gonna go left. If it's bigger, we're gonna go right. For example, I have a simple binary search tree here with a root node of 4. Let's imagine that 5 is not here and we want to insert 5 in our data structure. Then we're gonna compare 5 with 4, the root node, and we can see that 5 is bigger than 4, so we're gonna go right. So 4.right equal to 5. Now imagine node 1 is not here and we want to insert it. We're gonna compare 1 with 4, and 1 is smaller than 4, so we go left. And then we have 4.left equal to 1. Next, let's imagine that 3 is not here, and we want to add 3 to our data structure. We're gonna compare 3 with 4, and it's smaller than 4, so we go left. We go left and we see 1. And 3 is bigger than 1, so we go right. And then we have 1.right equal to 3. That's how we insert data into our tree. Now you might notice, because of this setup, the farthest left node is the mean node in our data structure. So if we want to find the minimum node, we can just keep going left until we cannot, and that's the node that we want. For example, in this case, we're gonna start with 4 and we're gonna go left to 1. And there's nothing left of 1, so we know that 1 is the minimum. And with that thinking, the farthest right node is the maximum node. So to find the max node, we can just keep going right until we cannot. And that node is our max node. In this example, we start at root 4 and we keep going right to 5. And at 5, we cannot go right anymore, so we know that 5 is the maximum node. Now our rules right here are gonna give us a very interesting property when we do search operation. That is, when we search for a node, we drop a sign of a tree in each iteration. Let's say that we want to search for 3. We start at root node 4. And because 3 is smaller than 4, we know that all the nodes on the left side of 4 is smaller than 4. So we're gonna go left. And just by doing so, we already dropped all the nodes on the other side of 4. And if our binary search tree is balanced, we are guaranteed to drop half of the remaining nodes at each iteration. In this example, we're gonna drop the right half from 4, and then we're gonna drop the left half from 1. That is a very fast iteration. It's gonna give us O log n time complexity if the tree is balanced. We're gonna see a vivid animation about this later. The delete operation is gonna include the search operation and the link and unlink operation for remaining nodes. Let's say that we want to delete 1. We're gonna unlink 4 to 1 by updating a left pointer of 4. Then we're gonna point left of 4 to 3. In reality, node 1 might have the left child. So choosing which node gonna be the child for is gonna take a little bit more effort. But we're not gonna be worried about it for now. Now let's have a look about search operation in binary search tree. This search operation is the same for balanced and unbalanced binary search tree. In this picture, we have a binary search tree here, and it happens to be a balanced tree. If we search for 3, you can see in the animation that it starts with 4. And because 3 is smaller than 4, so it decides to go left. By going left, it's already dropped half of the tree here. After going left, it sees 2. And because 3 is bigger than 2, so it decides to go right. And again, by doing so, it's also dropped half of the remaining tree, which is 1. And after going right, it sees 3 and it's returned 3. Again, because this tree is balanced, so we are able to drop half of the tree so fast. We only need to visit 3 nodes to find the node that we're looking for. Next, let's talk about binary search tree without self-balancing mechanism. Without self-balancing, the order that we insert and delete the nodes will decide how the tree look like. The tree will become unbalanced after one or a few insert or delete operations. And in the worst case scenario, the binary search tree is gonna look like a linked list. Let's have a look at a two extreme example of binary search tree insertion. The nodes in our tree are going to be 1, 2, 3, 4. And for the first example, we're going to insert 1, 2, 3, 4 in that sequence. So we insert 1, insert 2, insert 3, and insert 4. As you can see here, our tree looks exactly like a linked list because it doesn't have self-balancing mechanism. And if I 5 for 4, it has to travel through all the nodes to reach to 4. So that's ON, and that's not very efficient. For comparison, I'm gonna create another tree with the same nodes, but with different inserting sequence. This time I'm gonna insert 3 first. Then we have 1, and we have 2, then we have 4. And you can see the shape of the tree looks totally different than the previous example. This is because I changed the sequence of inserting the node into the tree. Now if we 5 for 4, it's gonna be much faster. But notice that if I delete 4, you can see that our tree now looks like a linked list. And the worst case scenario for tree operation is gonna be ON. And that's not what we want. That's why next, we're gonna introduce a self-balancing mechanism for our binary search tree. As we already learned before, a balanced binary search tree is the tree that has left and right subtrees of every node differ in height by no more than 1. And because of this property, whenever we drop a side of a node, we roughly drop half of the nodes. And that's how it helps to make our operations much faster. So a binary search tree with self-balancing mechanism will automatically run balancing method after changes on delete and insert. And these balancing methods take O log n time complexity. This will guarantee that our tree is always balanced. There are two popular balancing algorithms for binary search tree. They are AVL and red-black algorithms. And the binary search tree are named after them as AVL tree and red-black tree, respectively. AVL tree is named after its inventors, Addison, Velsky, and Landis. It rebalances the tree by a method called tree rotation, and we're gonna see an animation about this later. Red-black balancing algorithm uses a color flag, red or black, for each node of the tree to make sure the tree remains balanced. We're not gonna discuss in detail how these algorithms work, but the main thing we need to remember is they both cost O log n time complexity. So for both AVL and red-black tree, we have O log n time complexity on insert, delete, and search operations. This is a huge improvement comparing to previous data structures, because for the first time we have O log n for all of the popular operations. Next, we're gonna see how AVL tree self-balancing mechanisms look like. What I'm gonna do is I'm gonna insert the nodes into the tree with the worst from 1 to 3 and so on. And we're gonna see AVL tree rotation in action. We're gonna insert 1, insert 2, insert 3. That is our first rotation. And you can see the tree is balanced. Now I'm gonna try a few more nodes. I'm gonna insert 4, insert 5. That is our second tree rotation. Our tree is also now balanced. Insert 6. That's another rotation, and as you can see, our tree is always balanced. And with a balanced tree, our operations are guaranteed to be O log n time complexity. Next, we're gonna learn how to build our binary search tree data structure. Now remember, this is a binary search tree without a self-balancing method. First, we're gonna have the structure of a node. The node structure looks exactly like the binary tree node structure. We have node data, and we have left child, and we have right child. And we have the structure of our binary search tree without self-balancing, of course. First, we only have root node. Then we have insert method to insert our data into the tree automatically. Tree operation uses a lot of recursions, and we will talk about recursion shortly after. So right now we're not gonna deep dive into these implementations. Next, we have find min, which is gonna return the minimum value of the binary search tree. We also have find max, which is gonna return the maximum value of the binary search tree. We also have a method to check if the data is within the binary search tree. And we have remove method, which is the delete operation to remove a node from the binary search tree. And we have tree traversal as pre-order, in-order, and post-order. And we will learn about them in details later. Now we have built our binary search tree data structure. Let's use this to host our binary search tree in the previous example. First, we're gonna insert the data into the tree. So we have node 6, node 4, node 8, node 1, node 5, and it will print the tree out. This is our tree data. Now let's try some operations. First, we find the minimum value, which is gonna give us 1. We find the max value, it's gonna give us 10. And we check if 100 is within the tree, and the answer is false. And if we check if 8 is within the tree, the answer is true. And these are the pre-order, in-order, and post-order traversal results. And we're gonna learn all about them later. This will conclude our tutorial today for balanced and unbalanced binary search tree. Thank you for watching, and I will see you in the next video.